So I'm Hubert Montas, right, from Fish Health Department of Bioengineering, University of Maryland, College Park, and for maybe the past 30 years, with a variety of colleagues, we've been developing diagnostic decision support systems to help get more bang for the buck from best management practices, essentially by targeting the BMPs to critical source areas and watersheds, and then and also maybe targeting social intervention to potentially low likelihood adoption areas. This works? Yeah, you can hear me? I don't speak loudly. All right, I can sing also a little bit. The systems have three major components: spatial database or geographic information system, some models of the dynamics of potential pollutants and water within the watersheds, and then a series of expert systems, a diagnosis expert system and a prescription expert system. The idea is to run the biodynamic models under a variety of climate scenarios to identify hotspots or critical source areas for various constituents in the watersheds of interest, run the diagnosis expert system for each critical source area to identify what are the most likely reasons for this particular area to be exporting either an excess amount of water or nitrogen, phosphorus, possibly sediments. And once we have this diagnosis established, run the prescription expert system to identify appropriate best management practices for each one of those critical source areas. After this, we have a desired plan for implementing best management practices that would maximize how much water quality gain we would get for the amount of investment in terms of implementing best management practices within a watershed. But we have to filter this through a adoption behavior model, meaning that the BMPs will be useful only if they are actually implemented by the folks that live, within the given area. And so this is based on some statistical analysis that colleagues do of people's behavior based on socioeconomic characteristics. And from that, then you get an idea of how much of your desired BMPs are going to be implemented, and then might be able to target intervention strategies to those places where the implementation of BMPs is less likely to be happening. This is part of the team of folks that have been involved in doing this work. So this is me, this is Paul Liesnam, who's down over there. Adele, who is sitting, a lot of people, I guess, know him. Graduate student Jason Reichenberger, and a series of other folks from UMBC. We're from College Park over here. More folks from College Park dealing with some social aspects, some extension people. And this is for the agricultural part of our study. We did urban and suburban also work with a slightly different team, which includes some other graduate students. Jennifer Dindinger over there, she's also part of some of the activities that we've been conducting. And then Kevin Brinson there from Delaware. We've been communicating about doing some extensions and working with the DIM system and DIOS, that he's the principal person on. All right, so climate change, we know in the Northeast, quite a bit of expected change in precipitation pattern. And so one question is, how does this affect the types of best management practice allocation plans that we're doing with diagnostic decision support systems? We can think about it in terms of design rainfall. Whenever we want to design something in engineering, including culverts, drainage systems for roads, whatever it is, we need some sort of design rainfall. And typically it's assumed that the statistics based on which the design rainfall is established are stationary. Art, I think, mentioned that this morning a little bit. And with climate change, then what happens is the isohyets, the curves of equal frequency distribution for rainfall, would be shifting. If it's warming that we have, then they would be shifting from the south towards the north, in at least the northeast, and then maybe something different in the southwest where things are drying up. So we're expecting, more rainfall to occur, and this is expecting to change the way in which we design most of this hydrologic work. The question for us here is, what about those best management practices that we're prescribing, with our systems that are so advanced technologically? Are they going to be robust against climate change, or are they going to be just not effective anymore? Are these BMPs not going to be effective anymore? And therefore, all these 30 years that we've spent, putting these systems together will have been for, nothing. We'll have to restart from scratch. Right, so it's a little bit like if you consider the potential change of the laws of physics, the laws of nature, whatever not. This climate change, this changing of design statistics, of design rainfall, it puts things into question. If say the gravitational constant was changing over time, and you were designing a chair one time, for an individual, when the gravitational constant is low and people are very, very, very big, the chair might look like this, and then later on, when gravity increases and people are shorter, the chair doesn't really fit anymore, right? So it's something similar, but totally different, of course, as the laws of physics are not actually changing in this particular case of climate change. So we did two investigations. First one that I'm going to talk about. First one, an agricultural watershed in the eastern shore of Maryland, 300 square kilometers, not far from Delaware. Actually, parts of the watershed extends into Delaware. For this, we used a single CMIP3 model, the GFDL CM21, that was developed in the US, and that was considered to have good predictive abilities, at least in the way it predicted past weather. But what we saw a little bit later is that it predicts a lot of rainfall for the future, a lot of increase. And therefore, it's kind of a worst case model, if you would. There's three SRES scenarios, B1, A1B, and A2. A2 kind of like business as usual if we continue with the same patterns of activity that we're currently having. What would the future climate look like? And we're looking at 50 and 100-year time horizons in our analysis, with a fixed threshold for identifying our critical source areas. There's different strategies we could use to adapt, say, the critical source areas that we identify for today's climate to what they might be in the future climate. And so a fixed threshold means that whatever the lowest export rate in kilograms per hectare, for example, of a given constituent that we identified today, we apply the same one in the future for identifying critical source areas. So that's what we're doing in this first case here for this particular watershed, the Greensboro watershed. Relatively flat. The soils are sandy, as Kevin was mentioning, for Delaware also. The land use is agricultural, at least about 30%. And for the expected response to climate change, I'm going to take my notes, right, because I want to make sure I give you the correct numbers. We're looking at an increase in rainfall of 25 to 30% for the three scenarios that we investigated. And at the outlet of our watershed, we have from 50 to 130% increase in either runoff, sediments, nitrogen, or phosphorus. So from an increase in rainfall that's predicted to be of 25 to 30%, we have an increase in constituents that is non-linearly related due to the various processes that cause these constituents to be generated. That will be from 50 to 130% more than current, in that particular watershed. So what does that mean in terms of critical source areas? Under the baseline, the current climate, this is for surface runoff, a small portion of the watershed is considered to be critical. It is essentially around 10% of the watershed area. and it generates about 30% of the runoff. But the idea is, again, if you focus BMPs to these areas, you get some major bang for the buck here. There's a 3-to-1 advantage ratio in targeting these particular areas. After 100 years of climate change in the high emission scenario for this particular model, 80% of the watershed area now would be considered, with our fixed threshold, a critical source area where you would need a best management practice to achieve potentially the same level of control. And this is, of course, highly excessive. I mean, we're not going to go and put BMPs on 80% of a watershed. I think this is not such a good idea. But that's what the analysis is telling us. This is a worst case scenario. For sediments, same type of situation. Today, critical source areas occupy maybe 15% of the watershed. But with this predictions for climate change under this model, GFDL, we would get 60 or 70%, 3 times more of the watershed's area that would be considered critical and in need of best management practices in order to produce the same water quality gains that we do today. For nitrogen, again, same idea, maybe 10% of the watershed under current climate being somewhat critical. And then with not the A2, the most severe scenario, but A1B, one that doesn't generate as intense rainstorms that favor surface runoff, but one that generates more rainfall volume, but slower rainfall intensity, such that it favors infiltration and leaching of nitrate. We get 4 times more area that would need to be targeted. And for phosphorus, it's 2.5 more area that would need to be targeted in 100 years, following this particular model. And what that means is, if we're placing best management practices on the critical source areas that we've identified for today's climate or today's weather, they're not going to be able to control the exports of either water or sediments or nitrogen or phosphorus under the future climate. We could design BMPs for the future climate, and then they would work today and into the future. But the cost, is expected to be relatively much more than if we focus on the smaller areas of today. It might be necessary. It depends a little bit on which type of constituent we're considering. Our second investigation was for a suburban watershed. The idea was to try to go and remove some of the limitations of the previous investigation. So here, this is in the Piedmont region. It's a little bit more slopey. It's a smaller watershed, but mostly we use 6 models, 6 different climate models, to get an idea of the uncertainty in the predictions for the change in critical source areas in the future. Models from different countries, they have different origins, so the likelihood that they use the same assumptions or that they produce the same basic prediction is less than if all the models that we chose came from the same place. For RCP scenarios, that's a term for CMIP5 models, release concentration pathways or representative concentration pathways, 2, 6, 4, 6, 6, and 8, 5, and it was Art, I think, this morning that also talked about some of these types of things. Again, 50 and 100-year time horizons, and we use both fixed TMDLs and a relative or a fixed threshold and a relative threshold to identify our critical source areas. So the limitation of the previous study, the investigation 1, we use a fixed threshold based on today's conditions to identify critical source areas into the future. That's consistent with the TMDL idea, the concept that there's a maximum load that you can put in a water body on a daily basis. This, for some constituents, it might be the case. For other constituents, maybe it's the concentration of the constituent in the water body that is critical. And so for those, if the amount of water that is generated by your watershed, surface runoff, increases by 100%, then the concentration of your constituent, if the mass is the same, will decrease by 50% or divided by 2. Right, so we wanted to see if by looking at relative thresholds, we get a different set of results for our identification of CSAs where the best management practices should be placed. So this is a picture of the watershed. This one has much larger slopes than the previous one. It's in the Piedmont rather than the coastal plains region. Not much agriculture. It's a suburban watershed, and the soils are more in the loamy to clay type of soil groups. The change that we're expecting to see for the 6 different models with the 4 release scenarios, each curve is for a different release scenario of carbon dioxide, if you would, averaged over the 6 models, indicate again increases of 10 to 20% for a rainfall increase that is commensurate for that particular watershed at the watershed's outlet. And when it comes to the CSAs, at the baseline, so under current climate, CSAs or critical source areas would be the red and orange zones. Here they occupy 10 to 20% of the watershed. With a fixed threshold, after climate change, we get to about double that. 40% of the watershed would need to receive best management practices in order to maintain what could be the water quality gains under current climate. But with the relative threshold that is looking at concentrations rather than mass of exported constituents, we get back to the original situation, something that is very much like the baseline case. Right? So the summary of this is as follows. For Maryland and the Northeast, the changing rainfall patterns, both volume and intensity, will give us more runoff, more sediments, more nitrogen, more phosphorus production at the outlet of our watersheds. Critical source areas will increase by 1.5 to 4 times for constituents that we need to control by mass rather than by concentration. That is, to be able to control them, we'll need BMPs that are much more spread spatially and therefore much more costly to implement. But in the case where we have constituents that we can control by concentration, that is, the concentration of them is the critical factor, then we're expecting similar area and locations of those CSAs relative to what we have by designing with the current climate. Right? So some economies, would arise if things can be controlled this way. So for that later case, social intervention plans as well as BMP plans that we derive today would be robust against climate change. But for the former case, which affects also water, the amount of water exported by the watershed will increase a lot. And therefore, for flood control, for example, we're going to need new designs that are going to be much more expensive. And that's it.
Thank you.